centripetal acceleration and force. When an object travels at constant speed in a circular motion, the velocity is constantly changing. Let's have a look at that more closely. The speed of an object as it moves round in a circle stays the same. Now, if you remember, speed is a scalar and it has only magnitude. That's size. Velocity, however, is a vector, and because it's a vector, it has size and direction. The velocity of an object moving around in a circle has a magnitude, a size, which is the same all the way around the circle, but its direction is constantly changing, as you can see. Because its direction is changing, then we can say that the object is accelerating. Usually in kinematics, this acceleration is due to the size changing, but in this case, particular to circular motion only, it's not the size that's changing, it's the direction. Let's have another look at that acceleration. If we imagine a curved path, like that, and we look at v1 and v2, but maybe just a split second later. This is how those two vectors would look. v1, which is the velocity at this point here, and v2, which would be the velocity at this point there. The two vectors are the same size, because remember, the magnitude of v1 and v2 have to be the same, but their direction is changed. Now we know that acceleration is the change in velocity, so it would be v2 minus v1 over time. So if we have a look at these two vectors, v1 and v2, and let's try and do exactly that. Let's try and subtract v1 from v2. Well, if we draw them, here is v2, and v1, which is plus in this direction, but we want to subtract it, so we draw it nose to tail from here in the opposite direction, but of the same magnitude as v2. Now, as you can see, we now have a resultant vector, which is this one, and this is the resultant vector of v2 minus v1. As you can see, it's approximately towards the center between the two vectors. It's pointing towards the center of the circle. And this is in fact the case. The acceleration of an object moving in a circular path is always to the center. Okay, so to sum it up, acceleration is defined as the rate of change of velocity, and in a circular route you can find this resultant not by subtracting the magnitudes, but by subtracting the directions, okay, by using vector subtraction. And I'll say it again, when an object is in circular motion, the acceleration is always directed towards the center of the circle. So now we're going to throw some formulas at you. Luckily for you, the derivations behind these two relationships involve all kind of mathematical lunacy, like differentiation and other nonsense. So you just get to use them and learn them. So here we have the formula for centripetal acceleration, which is in terms of meters per second squared, and the formula is acceleration is equal to v squared over r. We also need to think about the angular motion, or in this case, angular acceleration. You have angular displacement, you have angular velocity or speed, and you also have the angular acceleration. And this is measured in radians per second squared. And the relationship is acceleration equals omega squared r. Now our formulas don't end there. We now need to think about the force that's actually keeping an object moving in a circle. This centripetal force is always towards the center. You've come across this when we've dealt with the motion of a charged particle in a circular path, and it's pretty much the same idea. An object in circular motion always experiences a force directed towards the center of a circle. Now that force could be a great many different types of forces. It could be gravitational, it could be tension in a string, it could be electrical. Regardless of what it is, it's always towards the center. If we have a force towards the center, how can we calculate it? Well, the resultant force equals mass times the acceleration in the direction of the force. Where did we get this from? Well, you did it last year. It's Newton's second law, sometimes disguised cunningly as force equals mass times acceleration. So how can we calculate that force? Well, can we calculate acceleration? We sure can. It's v squared over r. So let's have a look. We now have two more formulas. We have centripetal acceleration, that would give us our force, and we can also use angular acceleration. So force equals mass times acceleration, mv squared over r, and this is the one you came across in magnetism, dealing with the path of a particle in a magnetic field. And this one's a little bit different, but it's the force due to angular acceleration, mv squared r. Now, which ones are you going to have to learn? Well, none of these at the moment, as they're all on the data booklet. However, there is one more formula that you need to know about. Again, it's also in the data booklet, but you do need to be able to derive it. And that's using acceleration equals v squared over r. If we consider that the speed of an object moving in a circle can be calculated simply by considering the total distance around that circle divided by the time or the period of rotation. You might remember period from waves, it's the time for one cycle. So let's have a look at V more closely. If you're going around in a circle, then the distance you're travelling is 2 pi r. And so the speed would be 2 pi r over t. That would be equal to your speed, your velocity in this case. V squared over r then would be equal to 4 pi squared r squared over t r. And that would give us acceleration. We would need to cancel the r's. So what we get is a final relationship for acceleration, which is 4 pi squared r over t. Again, this is also on the data booklet, but it's very much worth knowing if you're ever given the period of rotation and the radius only. Here's a quick question for you. Identify the type of centripetal force acting in the two situations below. Have a think. Yes, gravitational force. in this one, and tension. Remember, there's also magnetic forces, electrical forces, and even frictional forces, something we'll go over in class.